Hello everyone, welcome to the fourth lecture of the subject CAD CAM. This is Mr. Suyog Patil, Assistant Professor in Department of Mechanical Engineering, Sharad Institute of Technology, College of Engineering at Rao, Itsalkandi. Today we are going to discuss the 2D and 3D transformations in CAD. First of all, we will see what is meant by transformations. As we know, in many of the practical problems, the components of the vector are known in one coordinate system. That is, let us see here, x1 and x2 is the one coordinate system in which this force F is acting. Okay, and we know this value of this force in this coordinate system x1 and x2, the vector component of the force. But it is necessary to find them in some other coordinate system. But this x1 dash and x2 dash is the second coordinate system in which we now want to know the component of the force F in this second coordinate system. Okay. Then the relationship between this component in one coordinate system and it is in the second coordinate system are called as transformation equations. This force F, the relationship in this coordinate first x1 and x1 dash is by some transformation equations. Okay, this relationship is called as transformation equations. Then again, as we know, the number of modeling software packages are available like CATIA, Unigraphics, Creo, SolidWorks, AutoCAD. Then again, all these softwares are used to create this part modeling. Okay, these softwares are used to model the components. Okay, then again we know while designing any component, number of iterations are required. That means many of the complex engineering systems we cannot design in one step only. Okay, so number of iterations or number of trials are required while designing that complex engineering problems or systems. Then again, this number of iterations are possible with the computers easily. When we use a computers or when we use CAD software packages, this number of iterations are easily possible. Then again, these drawings are created in these softwares like CATIA, Unigraphics, Creo. Okay, these softwares has a database. It's a separate database. That means in their software database, the already some models are created with the help of these equations. Okay, as we seen in the previous equation in geometrical modeling. So mathematical equations are stored. So these software database can be modified by some mathematical operations called as transformations. For example, all these softwares are built with some matrix transformation equations. Okay, so these mathematical operations are called as transformations. Likewise, or again we can say, as we know in this CATIA, Unigraphics, Creo, SolidWorks softwares, we can create a line, we can create a rectangle, circle or any other entities. Okay, and we want to shift that entity from one position to other position, or we want to copy that entity, or we want to delete it. Okay, we want to erase it, trim it. Okay, likewise these operations are carried out, or again we want to rotate it through an angle, certain angle theta. Okay, so these operations are carried out in the database. Okay, so mathematical operations will be there. So these operations are called as transformations. Okay, then a geometric transformation is an operation that modifies its shape, size, position, orientation, etc. with respect to the current configuration. Okay. So this geometrical transformation means if we want to change the size or enlarge the size, scaling is possible, rotation. Okay, then translate the object from one position to the other position. Okay, this geometrical transformation is required. Then this geometrical transformation can be classified into these basics class. that is translation, rotation, scaling, reflection, shear. Okay. And translation means moving an object from one location or one position to the other position, from this x1 position to the x2 position. When we move an object from one position to the other position, it is called as translation. Rotation. To create entities arranged in circular arrays, this rotation is required. Or when we want to rotate an object from a position x1 to a position x2 through an angle theta. Okay, so this rotation is required. The scaling. The scaling alters the size of the object. That means we can reduce the size of the object as well as we can enlarge the size of the object very easily with this scaling transformation. Similarly, reflection is there to mirror the object, or when we produce one object in this coordinate system and when we want to create another object in the same, in that case this reflection can be used or mirror option can be used. Then shear, this transformation causes image to the slant. Shear operation is there. As we know, this all the softwares are built with matrix multiplication formats, which helps for the transformation. These equations, transformation equations are built with the matrix multiplication formats in all these softwares. Now, again there are 2D and 3D transformations are there. So first of all, we will see 2D transformation. When this transformation is carried out in two or when it is carried out in two dimensions, and it is called as 2D transformation, and when it is carried out in three dimensions or three coordinate system, that is say x, y, z, it is called a 3D transformation. Then 2D object is represented by point and line or curve, then join them. Okay. So again, these transformations can be applied only to the points defining the lines, okay, or in two dimensions only. Let us say any point A with coordinates x and y is represented by a column vector 2 by 1. Okay, so we can represent a 2D transformation by using a 2 by 2 matrix, that is A in B, C and D. Okay, this is called a transformation matrix T. Okay, when we want to translate a object or when we want to transform a object, either it may be translation, rotation, scaling. Okay, so it is required in two-dimensional transformation, it is required a 2 by 2 translation matrix. We will see in detail. So first of all, in translation means moving an object is called as translation. Okay, for example, we can see this is the one rectangle here which is at origin. Okay, and when we want to translate this object from this position to this position, let us say from this origin to this position, this object is translated. Or again here in this example, we can see this object is translated from this origin to this another position. Okay, that means it is moved. When we translate a point by adding to the x and y coordinates respectively, the amount the point should be shifted in the x and y directions. We translate an object by translating each vertex in the object. That means the coordinates of this new point position P2, okay, this object is translated from this original position P1 to this position P2. Okay, coordinates of this position point P1 are x1 and y1. Okay, and now it is translated to this position P2, and coordinates of the P2 are x1, this x1 plus this certain tx, okay, and y1, this y1 plus this certain distance ty. Okay, so the coordinates of this P2 are x1 plus tx, y1 plus ty. Okay, so this Tx and Ty, this is called as transformation matrix. Okay, so therefore this x new coordinates x1, new coordinates xy, okay, are calculated by using this x plus a, x and y plus b. So this is called as transformation matrix. Okay, so this program is used to shift or to move any entity, that is point, line or rectangle, etc. So therefore in this translation, this coordinates of this new position P2 is equals to the coordinates of the initial position P1 plus this translation matrix, transformation matrix T. Okay, so in this translation, this matrix is added. Okay, that means initial coordinates x1 plus this translation matrix is added. Now similarly rotation about the origin. Suppose this is x1 and y1. This is point P having coordinates x1 and y1. Okay. Now if I want to rotate this point P by an angle this b, okay, by an angle, certain angle b, and this position or the coordinates of this rotated position x2 and y2. Okay, to rotate a line or a polygon or this uh, point, okay, we must rotate each of the vertices. Okay, so therefore we have to rotate the vertices of all the vertices of these lines from this p1 to position p2, okay, by an angle b. To rotate point x1 y1 to point x2 y2, so again some transformation matrix is required here. Okay, so we will see the equations of this transformation matrix. So as we know from this graph or axis, so this is the length of r and this is the distance y. Okay, this is the distance y1 and this horizontal distance is called as x1. Okay, this is x1 from this point to axis y. Okay, now as we know, sine of this a is equals to sine of this angle a is equals to this y1 divided by this r. Okay, sine of a, and cos of this angle a is equals to this x1 divided by r. Okay, similarly sine of this angle a plus this angle b, sine of a plus b is equals to this y2 divided by this radius r, and cos of a plus b is equals to x2 divided by this r, x2 divided by r. Okay, as we know this, this double angle formula, sin a plus b is equals to sin a cos b plus cos a into sin b, and cos a plus b is equals to cos a into cos b minus sin a into sin b. Okay, these are the standard formulas. But in the previous slide, as we know this, sin a plus b is equals to y2 by r and cos a plus b is equals to x2 divided by r. So when we put these values, okay, so we will get this sin a plus b is equals to y2 divided by r, okay, is equals to y1 divided by r, sin a is equals to y1 divided by r into cos b plus cos of a is equals to x1 divided by r into sin b. Okay, so after simplifying this, when we multiply by r to both the sides of equation, r will get cancelled here. Okay, and therefore we will get this y2 is equals to y1 into cos b plus x1 into sin b. Okay, so therefore this y2 is equals to y1 into cos b plus x1 into sin b. Okay, so this y2 means this second coordinate. Okay, this second coordinate of this line is equals to this equation. We got this equation y1 cos b plus x1 sin b. Okay, in the same way we can calculate this x2 also. Okay, in this equation when we put all these values of cos a plus b, cos a and sin a, we will get this value of x2 is equals to x1 cos b minus y1 into sin b. Okay, so therefore these are the x1, x2 and y2 are the new coordinates of this line. Okay, when we rotate this line by an angle, certain angle beta about this origin O. Now again, so therefore this, when we write these equations x2 and y2 in terms of x1 and y1, okay, so we will get one matrix, that is cos theta sin theta minus sin theta cos theta. Okay, so this matrix is called as transformation matrix. Okay, this matrix is called as transformation matrix. So therefore this x, original coordinates x and y, are multiplied by this transformation matrix. So we will get this new matrix, that is x cos theta plus y sin theta minus x sin theta plus y cos theta, and these are nothing but the x2 and y2. Okay, so therefore this x2 and y2 new positions, we will get these new positions by multiplying this transformation matrix here, okay, to the original matrix. So this is called as transformation matrix, which is used to rotate the object. Okay, then scaling. Okay, now scaling means changing the size of an object is called as scale. Okay, we, if we want to enlarge the scale or enlarge this object, okay, here we can see the object is enlarged here. Okay, we scale up an object by scaling the x and y coordinates of each vertex. Okay, so therefore we have to multiply some value here. Okay, and we have to scale up this object. So suppose the coordinates of this point P2 or object P2 coordinates are P2. Okay, so therefore we can calculate these coordinates of this point P2 is equals to initial coordinates P1 and some multiplication matrix S. Okay, so it is called a transformation matrix S. Okay, so therefore this S is equals to Sx0 and 0 in Sy, or again here we can see a into a0 0 b is the S matrix, that is transformation matrix. Okay, so therefore the new coordinates of new position P2 is equals to ax and by are the coordinates of the new position, okay, or scaled object. So therefore this matrix is equals to initial matrix xy into this transformation matrix. By multiplying this matrix, we will get this new position. Now this is all about the 2D transformation. In two-dimensional transformation, two coordinates are required to, or this 2 by 2 matrix is used to transform. Okay, but now in case of this three-dimensional transformation, 3D transformation, a point, 3D point is represented by x, y, z coordinates. Okay, so x, y, and z coordinates are the coordinates of this 3D point. Again, we will still use column vectors to represent the points in 3D transformations as well as. So again, homogeneous coordinate of the 3 point is required. So therefore here 1 is added in case, because of this homogeneous coordinates. Okay, in this it is required in 3D transformation. Okay, so therefore here, because of this one, so transformation in 3D transformation will be performed using 4 by 4 matrix. Okay, so we will see therefore, as we seen, the translation means moving an object from one position to the other position. Okay, and now we want to calculate the location, or we want to calculate the coordinates of this second position of this object, that is xy, x dash, y dash, z dash and 1. Okay, which is equals to, again to calculate this coordinates of this new position, so transformation matrix is required, and this 1 0 0 tx 0 1 ty 001tx 0001. Okay, the transformation matrix in 3D for the translation, and x, y, z and 1 is the original coordinates of the object. Okay, by multiplying this we will get the new coordinates here. Then in case of the scaling transformation, the new coordinates x dash, y dash, z dash and 1 can be calculated by using this scaling matrix. Okay, that is sx 0 0 0 0 sy 0 0 0 0 s2 sz 0 0 0 0 1. Okay, this is the matrix transformation matrix used to calculate the new coordinates in scaling transformation. Then again, when we want to rotate an object in 3D about an x-axis, okay, about x-axis, the x dash will remain same. Okay, the coordinate of x dash will be same as the x, but the coordinate y dash and z dash will change. Okay, when we rotate an object about x-axis. So therefore this y dash will become y into cos of gamma minus z into sine of gamma, and z dash is equals to y into sine of gamma plus z into cos of gamma, where the gamma is the angle of rotation. Okay, when we rotate by angle amount gamma. Okay, so therefore, this new coordinates of this rotated object, that is x dash, y dash, z dash and 1, we can calculate these new coordinates by multiplying this transformation matrix into original matrix. Okay, so this original matrix x, y, z into 1, and this transformation matrix contains 1 0 0 0 0. Instead of this 1, this will come cos of gamma. Okay, minus sine of gamma here. Then again z dash is equals to y sine of gamma, so 0 into sine of gamma here, and this cos of gamma will come here, again 0 0 0 0 and 1. So this is the transformation matrix for rotation about x-axis. Okay, when we want to rotate any object or any entity about y-axis, okay, the y dash will remain same as y. Okay, the coordinate of y will not change, but x and z will change here. Okay, so therefore z dash will become z into cos of beta minus x into sin beta, and x dash is equals to z into sin beta plus x into cos of beta, where beta is the angle of rotation by which we rotated an object. Okay, so therefore the final position or final coordinates of this object x dash, y dash, z dash is equals to, so therefore here x is equals to sine of beta plus x into cos beta, and z dash is equals to z cos of beta and sine of minus sine of beta. Okay, so therefore this will come here, the cos of beta 0, sine of beta 0, this matrix will come. Okay, and by multiplying this transformation matrix to this original matrix xyz1, so we will get this final matrix of the rotation about y-axis. Similarly, when we rotate this object about z-axis, z will remain same, and x and y coordinates will change here. Okay, according to these equations, x into cos of alpha minus y into sin alpha, x into sin of alpha plus y into cos of alpha. Okay, so therefore this matrix will come here. So this final position of this object x dash, y dash, z dash is equals to cos of alpha minus sin alpha 0 0, sin alpha cos alpha 0 0 0 0 1 0 0 0 0 1. Okay, this is the transformation matrix when it is multiplied to this original matrix x y z and 1. Okay, so we will get this final position of the matrix about rotated about z axis. So this is all about the 2D and 3D transformations in software, CAD software package. Thank you so much. Friends, thanks for watching this video. If you like this video, please share, comment and like this video. Then subscribe to my YouTube channel and click on the bell icon to get notified for more videos on this CAD/CAM subject. And thanks for watching. Thank you so much.